Hi again. This time I'm going to talk about an LED device operating as a photodiode, and it's had a bunch of LEDs lying around of different colors, and since they have different colors, they operate of different band gap voltages in terms of the way the band structure is for to generate the various colors. So I thought they would have, if you use them as a photodiode, they have different sensitivities or responsivities as well. So I wanted to experiment with that, and so I'm going to talk about a little bit about an LED, how it works, and then we'll talk about the circuit that can be used to detect the current that comes out of it when incident light hits it, and a few other things about the waveforms that are in this particular circuit. So the first thing is the LED itself. It's basically a diode kind of a device. It's operating when it's operating as an LED transmitter or generating light. You're operating in the forward region over here, where the anode is more positive than the cathode, and that the forward voltage is where the LED begins to emit light. Above that, the current starts to quickly increase as exponentially, and so normally they bias these LEDs around 10, 20 or 30 milliamps at most for normal light emitting diodes. So but we are in this particular experiment, we are going to look at the LED operating in the reverse bias, where it acts like a photodiode. And so normally when there's no light, it's the reverse bias or reverse current is very small, in the order of maybe nanoamps or even less, and that's the dark current basically, which is the light produced, also the current produced when there's no light shining on the LED. And once you start put some light on the LED, it starts to the current starts to increase, and that is the effect of the electron hole pairs being generated and being swept into the junction, past the junction into the contacts, and so those are collected and then they travel in the external circuit, which produces the current. And that is, you can see the reverse bias, the reverse characteristic begins to change, and it basically increases the amount of current that is seen as you change the light. So the light intensity affects how far down this goes, this curve. Now to measure this particular current, we need to operate in the reverse bias, which means the cathode is going to be more positive than the anode, and in the circuit shown above, we're going to operate in this region of the reverse bias voltage regime, which is in this case minus VDD to something called minus Vmin, which is the minimum we want to use it before it becomes the output of this circuit becomes a little bit nonlinear. So in terms of the the LED model itself, it looks something like this, with a standard diode and a photonic current source, which is IPH, and there's two parasitic elements, R shunt and the C shunt capacitance. The capacitance really comes into effect when you're talking about dynamic operation, AC signals and modulation and so on. So in this particular example, we are going to use DC light, light that is not changing, and so we won't have to worry about the C shunt as such, or the bandwidth of this device. Now as far as the circuit is concerned, we still have the LED here, which is operating in reverse bias. As you can see, the VDD is on top, so this becomes more positive when the switch is turned on. It charges up this integration cap, also reverse biases this LED to the plus VDD voltage here. So there's a VDD voltage across this particular LED when this switch is turned on. Now when the switch is turned off, it's a very brief reset that you have. What happens is this node becomes high impedance because this is a gate of the NMOS transistor, and the only other place where the current can go is really into the discharge out of the capacitor into the LED as the light shines on it. If you have a very low light, of course the amount of current that can be discharged through the LED is very small, and so that essentially, if you look at the curve on this side over here, the blue curve is actually the integration voltage. It starts at VDD, which is up here, and starts to decay linearly as the light starts to bleed off, the charge of this capacitor, and that current is basically causing the voltage to drop off. At some point this reset pulse comes in and again pulls this node back to VDD, and then the cycle starts all over again. So this is the curve. If you have a constant light shining on this, we will have a discharge and a reset and discharge and reset and so on. Now if you want to measure this voltage, if you put any kind of a probe on this, considering that this current here in the order of nanoamps, it will not be able to drive that, and immediately the voltage on this node will collapse. So in order to avoid that, we have a source follower here, and the source follower is an NMOS device. With the source side we have a series resistance RS. Essentially the gain of this particular structure, where you have the input coming in here and the output coming at the source, is given by this equation, which is GMN, that is the NMOS device, RS over 1 plus GMN RS. So if you have GMN, which is typically going to be large if you have a decent amount of current flowing through this device, GMN becomes much larger than 1 over RS, and therefore you can ignore the 1 term here and you have a gain of approximately 1. So in this particular example, we have the GM of this transistor, and the data sheet was given to be around 320 millisiemens at 400 milliamps, or 200 milliamps, I'm sorry, and the current here in this actual circuit is 1 milliamp. So if you take the square root of 200, which is a reduction in the GM based on the current change, you would get a GM for this particular circuit of around 15 or 14 roughly millisiemens, and RS is around 4.7K. so if you take the product of that, this is close to 100, and basically the 1 will drop out of the equation and you get a gain of approximately 1. Actually in this case it would be 0.986 or 0.99 almost. So effectively you have a gain of 1. The only thing that happens is that the VGS of this transistor is quite large. It's about 2 volts or 2.5 volts. So any voltage over here will be dropped down by that VGS here. The VGS is approximately equal to the VT of this transistor. So in that case you'll see that the drop in this output voltage Vout is about 2 volts or so lower than the voltage on Vint. That you can see here, as it basically tracks the same wave, the same slope and everything, but except shifted down by that amount. The only problem is if you run this, discharge this cap completely, then you effectively turn off this device. So you want to operate at some voltage, several volts above the minimum threshold voltage for this thing. So in this particular example, I'm keeping this Vmin around I think 4 or 5 volts just to be safe. So you won't discharge it beyond this. You'll immediately reset by the time it gets there. So what happens if you have a very large current in this diode LED? So in that case you would have to increase the capacitor, so you take a longer time to discharge it, and so you have more time to essentially let that voltage drop down to the same value before it reset it. The other option is you can change the frequency. So if you make this frequency higher, you can again do this quicker, and so if it's a very sharp fall off because you have a large light and this amount of discharge is faster, then you can do the resets more often, and then so you get a different frequency out of this thing, but it will still discharge linearly down to that value before you reset it. So that's the different trade-offs you have when you have different LEDs. You'll have to play around with the C-int. In this case I'm going to keep the frequency the constant. I'm just going to play with the integration capacitor mostly. So in this experiment, what I'm going to be doing is trying different LEDs. Like I mentioned, I have 5 different LEDs, blue, green, red, one which is I think almost like a UV LED, and yellow. And then I'm going to try different C-int values, basically to see what happens if I let it saturate down and hit 0, at which point this NMOS device will collapse, and you'll see that it's actually not usable at that point, the output voltage. And also see some effect of light modulation, which is going to be occurring in this environment due to various reasons. I'll tell you about those more. Anyhow, I think that basically wraps up this part of the video, and next I would like to go into the setup and show you what I've got here. So as far as the setup, I have a power supply over here, which is a 10 volt DC supply, which is driving the VDD of that circuit I showed earlier. And here's the board, the circuit board, which I soldered these components onto, and that's all I need is a scope to measure the sawtooth waveform that's going to come out, and the reset. I'll look at those two signals, and I will synchronize the oscilloscope on the reset signal, which is a very nice signal to sync on. So as far as the components, this is the PMOS pull-up reset transistor over here, and this is the NMOS source follower device. There's the resistor, the 4.7K, and these two terminals over here are the capacitor where I'm going to, which is currently it's got a small capacitor there, I believe a 330 picofarad capacitor. And then the yellow wire is going to be the gate control, which is coming off my AWG over there, and what else? And then the power supply is the red trace, the red wire, and the black wire is the ground. And these two wires coming off are the connections to the LED, which is over here, a blue one at this moment. You have to make sure you put them in the reverse bias. That means the positive has to go to ground, and the negative cathode has to go to the capacitor integration node. So now I'm going to turn on the power supply and also the AWG, and then we'll turn on the light and see what happens. This is the setup with the reset not being active, and you can see the output voltage is sitting very close to ground. That's the ground level is right here on the yellow curve, and it's got some ripple on this, basically some noise, I guess, or this room lighting has got some 60 Hertz component in it, possibly that's affecting that. But it's almost down to zero because the capacitor is discharged, there's no resets going on, and so nothing to pull up the voltage to supply, which is 10 volts. And the blue curve over here is going to be the reset pulses, and they're going to be very, very narrow, an order of 10 microseconds, and the total integration time is about 16 or so milliseconds, and you'll see that's barely going to be a very short spike in that waveform. So I'm going to turn on the reset now. So there you have the reset turned on. There is still that modulation you can see happening, but now it's synchronized to the 60 Hertz. Roughly this reset is occurring at this line frequency of the mains, also at 60 Hertz, and this is almost synchronous with that, and you can see there's some amount of movement on this left to right, which is because of the frequency difference between the AWG and what the actual mains frequency is, which is creating the lighting in this room. Now if I turn on the bright light over here on the blue LED, you'll see, let's see what happens. So with a 330 picofarad capacitor, you can see that a very large voltage drop, order of 5 volts or so, as I mentioned. And so it's possible that it's not quite reached the ground level, which is over here. That means this is operating in a fairly good operating region for us to be able to measure this without any distortion on the source follower itself. Now I'm going to do the green LED, and let's see what happens here. Okay, we have a very good swing, almost 4 volts, and it's linear for the most part, except it's towards the middle it starts to droop off a little bit more quickly. Other than that, I think it's a very solid linear output from this green LED. And now for the red LED. Oh wow, now look at that. That is going to be fully saturated. As you can see, the waveform actually has hit the rails, the bottom rail, and that means I need to increase the capacitor a little bit to be able to actually measure this properly, but I'm losing out quite a bit of the signal because of the capacitance is completely full in terms of the charge, and so I'm going to do that later. But if I do the next LED, which is going to be the yellow, it's even more sensitive to light than the red one, so I expect that to also go fully to zero. So let's look at that as well. So now I've got the yellow LED in place, Yeah, and as you can see again, it's fully saturated almost halfway through the integration portion, even better than the red LED in terms of sensitivity. So what I'm going to do is to put a 1 nanofarad cap here and see if I can bring that voltage up to a smaller swing, so make it a little bit more measurable in terms of total amount of charge that is being dumped onto this dumped out of the capacitor in a given cycle. So here's the yellow LED now with the 1 nanofarad capacitor, and as you can see, this one is made it to about 1.5 volts or so, and again extremely linear over the range, and a very nice performance in terms of the, you can see it's extremely linear. And if you measure the voltage down here and integrate that amount of charge, you can calculate the current that is being provided by the LED based on the capacitor and the voltage change. So this is an excellent measurement that one can actually use to characterize this LED. Okay, so now I have replaced the capacitor with a 3 nanofarad capacitor, and let's turn on the light. Now as you can see, the swing is actually about 2.5 volts or so, definitely more measurable. If I zoom in there, you'll be able to see that clearly. That looks pretty good, again very linear, and this is the best LED for measuring light. So far we looked at different LEDs and different integration caps. We looked at the 3 nanofarad, 1 nanofarad and a 330 picofarad cap, and several LEDs. It's more interesting when you have a large amount of current. You can see it saturating, and to be able to get rid of the saturation, you increase the capacitance value as I did. But here's another thing I want to show you is modulation. So this is the full blast white light coming onto this LED, and you can see as I move the light around, you can see the amount of intensity changes because of the angle or the distance or the focusing of the lens onto the photodiode in there, or the LED inside, that changes the current that is coming out, and it's very clearly able to move that around. Now if I reduce the light using this position, there's something interesting happening over here, and this is actually some modulation going on inside this flashlight, which is creating the dimming effect, and that modulation is actually measurable, and I can do that by stopping the trace over here and then measuring the distance of that jagged pulse coming out of that thing. So what I'm going to do is to measure that and come up with the frequency at which this is being modulated. So here's a close-up, little bit better close-up of that waveform, and it's you can see that this stair-step kind of effect over here is actually the modulation that's going on, where stopping the light and then allowing the light to go through, and so effectively dims the flashlight. So the repetition rate is basically this edge to this edge, and that frequency turns out to be 330 Hertz according to this measurement here. So it's quite interesting that you can do that, and it's not obviously visible to us, but the LED is certainly able to pick it up and show that as a current change in the output of the amplifier. So here's the white or UV LED. I guess it's one of the extremely high band gap type LEDs here, and you can see I have put in the minimum capacitor of 30 puff. There's already some parasitic capacitance on the NMOS device of around 30 to 60 picofarad, I believe, and that's going to add somewhat to this capacitance and effectively increase the cap on that integration node. But you can see the effect of lighting and leakage or other AC hum is basically showing up on this signal now. If I turn on the light, you can see actually it does respond, and is quite a bit of response, but it's a very weak LED, and this is at the 30 puff integration, so it's It's not a very big signal. I would say it's in the order of about 3.76 volts. Um, Not a very accurate measurement because it's not linear at all, and it's being interfered with other sources of light and disturbances here. So here are the results of my measurements. So before I get into the actual values, talk about some of the estimations and assumptions. So the first estimation I had to make was the area of the detector, which turned out to be probably the most inaccurate in terms of what I could judge. And I assumed that was around 0.2 millimeter by 0.2 millimeter based on the dimensions I was able to see using a lens or something like that. So that was 0.004 centimeter square. The input power from the light source was in the high intensity position was around 14 milliwatt per centimeter square, which was measured at 600 nanometer, and the low intensity power was 7 milliwatt uh, per centimeter square, again at the same wavelength. And the time, integration time, was 1 over the reset frequency, which was 60 hertz, so came out to be 16.67 milliseconds. Now a couple of formulas you need to know. One is to how to calculate the LED current. So that's basically the integration capacitance times the output voltage, which is the charge, divided by the time, which is the integration time. So that was 16.67 milliseconds. And to get the responsivity, you have to take this current, LED current, and divide it by the area of the detector and the power input. Uh, so that is going to be the values I just discussed here. And as you increase the area, of course, you're going to have a decreased responsivity. And so similarly with the power, so if you minimize those two, you get a higher responsivity. So anyway, getting into the results, the first one was a yellow LED, which was using the highest integration capacitance of 3 nanofarad, and the high intensity position we had 7.12 volts, LED current of 1.28 microamps, with a responsivity of 228.9, which is a pretty large number for LED as using as a photodetector, because commercial actual photodetectors are somewhere in the neighborhood of 400 to 500 amps per watt. So this compares very well with a photodetector that you can buy, much more expensive of course. Now the red LEDs were a little bit weaker in terms of responsivity, so I did two measurements with the high and low power settings at using an integration capacitance of 1000 picofarad or 1 nanofarad, and I should have gotten um, the same responsivity because I was decreasing the light, so I should have seen exactly the same change in the voltage. Uh, I think the reason for the discrepancy is probably I didn't do the experiment at the same time. I must have moved the light, or the LED position was a little bit different in both the cases. So I don't trust these results, but it gives you a general idea that uh, changing the power, light power, should basically reduce the intense voltage swing correspondingly to get you the same responsivity. The next LED I measured was a green LED at the same integration capacitance and a higher power setting of the light, and this was about 4 times weaker than the red LED, or maybe 3 times weaker, so giving a current of about 84 nanoamperes, considerably less than the others, and so the responsivity came out to be 15. And finally the blue LED was the least responsive of the four LEDs that we measured, and I did it at two different integration capacitance, and in this case I got almost the same responsivity, which makes sense. So here I decreased the capacitance by a factor of almost 3, but I got 3 times the voltage, so basically that effectively produced the same amount of charge on the capacitors. So while this was a fairly simple experiment to do, I did spend a bit of time to get this set up right and get them good waveforms and so on. And the other thing, of course, we learned was that the modulation effects on the LED and how it could be used as a means to measure varying signals, light signals that is. And so this is probably something I can use to do some new experiments with and learn some more about these LEDs. So I hope you enjoyed this video, and look forward to next video with you guys. Thank you. Bye bye.